Thank you. So this talks about reference counting deeply immutable data structures with cycles. So this talk is very similar in style to the previous talk. So I'm going to start by unpacking this deeply technical title. So what do I mean by immutable data structures? So immutable data structures, so here you've got your sort of applications of persistent data structures, functional languages, or like concurrency, where you might want to share things between threads and you don't, each thread can be accessing it at the same time, and if there's no mutation, everything gets much easier. So your shared data is much easier if everything's immutable. And then there's sort of, in the immutable data structure world, there's sometimes things are just constructed immutably. So you might have everything's immutable from the start, sort of you just allocate it and everything, you know what it is. Or you might have some operation that turns it immutable at some point in the future. So some languages have something like freeze, sort of this object graph will no longer move, change at all. And that can be sort of at the level of an individual object, or it can be deeply immutable data structures. So that, I mean that, I'm going to have to hold this, I think. That means that everything you can reach is immutable. So you could have some object graph. This object graph has some objects in it. So if A, oh no, if A is deeply immutable, then it means everything it can reach is going to be immutable. So, reference counting. So in this audience, hopefully everyone knows what reference counting is. You keep the in degree of an object. Here's that same graph. It's got some numbers on it. If we take away a pointer, a number goes down, the object goes away, more numbers go down, but the objects go away, and everything gets collected. So reference counting, awesome, love it. Reference counting with cycles. So life gets a bit harder. Let's add a few more edges. And now reference counts go up a little bit. And now if we want to collect this, oh, it doesn't work. So reference counting with cycles, classic problem. Everyone hopefully knows that. So in this talk, I'm going to talk about reference counting deeply immutable data structures with cycles. So the research question is, if we have deeply immutable data structures, can we make reference counting collect those data structures even in the presence of cycles? So the observation is that if we have deeply immutable data structures, then the cycles do not change. So we might be able to afford to do a slightly more expensive operation up front. And for those of you who remember sort of your undergraduate data structure and algorithms, strongly connected components are a nice way of factoring an arbitrary graph into an equivalence relation and a DAG. So what I mean is that every graph can be turned into a DAG, so something that can be reference counted nicely, and an equivalence relation. So basically you've got little groups of objects. So that means if we do reference counting at the level of SCCs, then it's safe to reference count an arbitrary graph. So here we've got that same picture. Now this has two strongly connected components. It has B, which is a strongly connected component with a single object, and A, C, D, E, which is a strongly connected component of 4 objects, because they could all reach each other. So in the paper, we present an algorithm, which I'm going to fly through in the time I have, which is basically, if you go to Wikipedia and read the path-based strongly connected component algorithms page, and then squint and think a bit about changing it so it does reference counting at the same time and fiddle a bit, so it uses union find rather than a slightly different data structure, you will get the rest of the paper. But what we do, basically, we're going to use union find in the algorithm. So this audience perhaps isn't as aware of union find as like the theorem proving people, but it's a good way of representing equivalence classes. You keep 2 operations around. One is tell me the representative is the equivalence class, so it gives you something you compare for equality. So you can ask 2 objects are in the same equivalence class, find their representative, ask if it's the same thing. If it is, then they're the same. And union, which basically allows you to merge 2 equivalence classes. So like the common algorithm for this is parent pointing trees. If we do basically our path-based union, path-based strongly connected components at the same time, we can generate reference counts as we go. And in the algorithm that I'm going to present on the next few slides, we're going to have a single field inside an object that represents the reference count, or that this is something we haven't visited yet, so unmarked, or a rank. And rank is a sort of technical thing from union find, so you have to do merging in a certain way. So it's keeping track of how large a strongly connected component you have. So the code fits on a slide, possibly not legibly, but on a slide. So we have a stack of tentative strongly connected components. So the algorithm sets up basically pending, which are all of the things we think could be strongly connected components that we've visited so far. And then every time round, we're going to basically call this freeze on an element, and it's basically a depth-first search. So we're going to look up the status of that particular object, which is this, like, either it's a rank or it's a reference count. A strongly connected component we've already found. It's got a reference count, or it's unmarked and we haven't visited it yet. So the first sort of case analysis of this is, so we look at the status and we see that it's unmarked, in which case this is our main DFS exploration of the graph. And then there's a pre-order step where we say, well, this is a new thing, so I'm going to make it its own strongly connected component and mark it sort of tentatively as a strongly connected component and put it in this set of, in this stack of them. And then I will look at all of its fields recursively, actual algorithm, not recursive. And then we do a post-order step, so on the way back out, we have to then say, okay, if we're still the top of the stack, then we can take ourselves off and we can say this is a completed strongly connected component. And then we get, if it's a completed one, it has a reference count of 1 because there's one entry into it. And then later on, we might add some more, which is what's going on. Sorry. Yeah, if we find, so, which is what's going on the bottom part, is when we find a back edge. A forwards edge. And then these, if we reach something on the stack of pending things, then we're going to pop back up because that's basically a back edge that we've determined through the path-based exploration. So that was perhaps a little abstract, so I have a pretty graph. This is also in the paper. It took up a whole page. So if you don't follow it here, you can follow it there or not. So we look at A. The depth first order is going to be alphabetical. So A goes to B, and it sees B. It goes, so what's going to happen here is it finds B. It has no children, so it doesn't have to do any work. And then it's going to see that it is still the top of pending, because pending is A and B. So that creates a strongly connected component with reference count 1. And that was very quick. So then we look at C, and we push C onto the pending stack. So we've got A and C. Then we go push D in, and we push D onto the pending stack. So we've got A, C, D. And then that sees B. So B now has an edge coming in, and that lands here. So that's, we found something that already has a reference count. So we've already found it, so we give it an extra count. And then we pop back out. So as we, sorry, which way did I go? So we followed the edge from D to C now. So C is on our pending stack. So that means we've created a back edge because we're looking at something we've already seen. So we'll merge those and we'll remove D from the pending stack. And then we pop back out. Sorry. Pop back out, but we're still in a pending state, so we've still got edges to look at. So we go to E. And then E sees that it's pointing to something that's on the pending stack A. So it unions those, and then it goes through this while loop here, popping back up until it finds the right thing. So it unions those, and then a bit more time, and the algorithm finishes, and it puts a reference count of 1 on this. So that gives us our basic calculation. You can probably find someone on Wikipedia, on like YouTube or something, doing a much better job of explaining path-based strongly connected components, but that's my attempt. So then we want to release something. We can say, we can create edges to intermediate points. Like we can point at B here, and now that has a reference count of 3, so we could have more indexes in. And we could drop a reference on A, and now this whole thing has to go away in one go. So that kind of needs to disappear. And what we really have to do is follow all of the edges to stay within the SCC before we follow edges that come out of the SCC. So we have to kind of effectively do a depth-first search where we prioritize internal to external edges. So So we implemented this. The algorithm is almost linear time. We're using union find, so that gives us a very, very slightly off linear time thing, but it's inverse Ackermann, so not very much. The performance, so what have we got? So here we've got running the code, basically, so we've got alloc. So if we're building, in this case, it's 5 minutes. Cool. Doubly linked list. So the blue line is for various sizes, how much it costs to allocate that with SNmalloc, see previous talk. And then we've got freezing cost. So this is the cost of going through that data structure and actually running this path-based strongly connected components on it. So you can see it's a bit more of an allocation. We also, in the runtime that we built, had a mark and sweep collector. So you can see that that's the orange line here. So it's a bit higher than that as well. But most of the examples we looked at, it was within double to 2.5 sort of cost. So freezing was about twice to 2.5 times the cost of actually doing a straightforward mark phase where it didn't collect anything. So just doing a depth first search over that graph, which it's quite similar in cost. As you might notice, things get slower as you get faster. So I was a bit worried about this because I was trying to present a paper on an almost linear time algorithm, and it got worse as it got bigger. So I was trying to work out why that was, and eventually I decided that machines have caches, and caches don't hold bigger workloads. So everything gets slower as you get bigger, and you can't show a graph that looks linear. So then I added these extra lines at the bottom, which are the number of steps followed by the find algorithm, which is linear, and it's perfectly linear. So the algorithm is linear, just machines aren't. In the paper, you can look at more graphs that all look pretty similar in terms of various different data structures with different levels of cyclicities and back edges, forwards edges. I think one of the interesting things is depending on the order of the fields can affect the cost, because sometimes, like with a doubly linked list, which one is it? This one is much worse than this one because it's following one of them's following the forwards edges first, and one of them's following the backwards edges first. And if you follow the backwards edges first, everything stays nice and compact. And if you follow the forwards edges first, it doubles the size of some of the stacks that you have to keep track of. Cool. So applications of this. So we were looking at this because we wanted to use it for shared immutable state. So in the Pony programming language, there's basically a way of freezing memory and then allowing you to share it between threads. But in there, they're using tracing GC, quite a challenging sort of thing that works across actors to do that. But you have to manage that memory in like managing it in a classic way. And we wanted to see if we could do something better. So sort of as part of this project I'm working on for memory management, we wanted to build this for that. So that's kind of where this came from. For functional languages, this could be quite interesting to replace some of the tracing GC stuff. In fact, Ryan's talk earlier when he was talking about the reference counting for the big old stuff and it not working well for cycles, I was like, ooh, I want to talk about that. So that might be interesting. We're currently prototyping this. We're sort of looking at Python and seeing if we could add something to Python because there's interesting reference counting going on. So if we added immutable state to Python, could we do this algorithm there? And then reviewer D, it wasn't B this time, asked, could we apply this to tracing GCs? And I think that's a really interesting question, which I don't have a good answer to. But to go back to the original question, if we restrict to deeply immutable data structures, can we make reference counting collect those data structures even in the presence of cycles? The answer is yes.
That was very interesting. And I agree with your enthusiasm for reference counting, of course. But there was something I missed, so I don't quite get what's happening here. So if you look at the picture you've got on the screen, just for example, the deeply immutable, that also refers to the references, or no?
So the topology is deeply mutable, but the reference counts can mutate. So you can create references into it.
Into it, from outside?
From outside, but you can't change anything it can reach.
Ah, okay. So then what I didn't get is that the algorithm you described sounded to be essentially a trace.
Yeah.
In which case, why not do a trace?
So because
the outside references are changing.
Because the outside references are changing.
That's the key thing I was missing. So the internal references are not changing, but the outside ones are, and then you want to know which ones you can kill when the outside references change.
Exactly, yeah. So it's when can I collect this stuff? So like if you have long-lived data structures that are deeply immutable, tracing, like, so in principle, right, with this sort of squinting, sort of seeing 2.5x, right? If you have to trace it more than a couple of times, then this would be a win.
Yeah.
Because you don't know when it goes away until that.
That was the next thing I was going to ask or suggest, is that green line there is a one-time cost, whereas the other ones are...
Precisely, yeah.
Okay,
other than the fact that when you introduce reference counting, then you've got reference counting manipulations, whereas with tracing you don't have those, so there's slightly more subtlety there. But
sure.
You're very aware of that.
Other questions? So the, I guess, have you thought about using this for like a general purpose language that has lots of mutation like Java, what that would look like in terms of speculations and misspeculations?
So after our reviews and thinking about our rebuttal, we did. So one thing I thought would be an interesting sort of design point is if you have sort of a generational kind of scheme. So your early generations you still do with as you would, but when you promote things to one of the sort of longer lived generations, you might apply this to then basically say, oh, well, I'll use reference counting for those older generations, and then periodically you'd have to do something to recalculate whether so it's always safe to use an incorrect strongly connected component graph, right? So if you connect things which aren't actually connected, it's safe, but you won't collect memory. So potentially there's memory that could be collected, but you won't. So, but that's kind of a generational hypothesis, right? You stop looking at old stuff because, wow, it's probably not going away now, is it? So this might be a way of getting some of that older stuff away quicker if there are cycles involved, or yeah. So that would be sort of my starting point, but I don't really have time to do it. But if anyone's interested in talking about it, I'm happy to.
I wonder also if this would be useful in the context of Rust, because there's a lot of information, type information about immutability, and then also Rust has a reference counting cycle collection problem that it doesn't guarantee collection of cycles. So I wonder.
Yeah, I haven't. The code's written in C++, but it could be written in Rust to do this. So yeah, I don't know if the immutability in Rust is deep, so in that sense, it wouldn't apply in the sort of way in which at least it's presented in the paper. But I think one of the reasons why we wanted to write an intellectual abstract on this is because we thought it was an interesting trick, and people might apply it in another way. So.
Time for one last question. Actually, it's time for the break. So I think we'll come back in 20 minutes at the hour, right? Thank you.